The BBC Studios, London, 1983. The camera is rolling. Christopher Sykes, one of Britain's most persistent science journalists, asks Richard Feynman a simple question. Can you explain in ordinary terms why magnets attract? Feynman stares at him for 11 seconds of dead air. Then he says something that makes Sykes visibly uncomfortable. I can't explain that attraction in terms of anything else you're familiar with, because I don't understand it in terms of anything else. The Nobel Prize-winning physicist who revolutionized quantum mechanics just admitted he doesn't understand magnets. But here's what Sykes didn't know, and what's buried in 17 pages of Feynman's lecture notes from Cornell. That answer was deliberate misdirection. Feynman understood magnetic fields better than almost anyone alive. What he was really saying would dismantle everything physics students are taught to believe. This comes from the documented BBC Horizon interview, The Pleasure of Finding Things Out, filmed months before Feynman's cancer diagnosis. The full exchange runs 4 minutes. Physics professors still show it to graduate students, but they always stop the tape at the wrong moment. They miss what Feynman says next, and more importantly, what he demonstrated in a 1964 Cornell lecture that was witnessed by over 200 students and recorded in Volume 2 of the Feynman Lectures on Physics. Because when you read Chapter 1 of that volume alongside his private correspondence with colleagues, a pattern emerges. Feynman wasn't just teaching electromagnetic theory differently, he was systematically undermining the way every textbook in the world explained fields. Cornell University, fall 1964. Feynman walks into Physics 227, Advanced Electromagnetism, and immediately erases the board. A student had drawn the classic diagram, field lines radiating from a charged particle, neat arrows curving through space. Standard visualization. Every freshman physics student knows it. Feynman stares at the drawing. Then he says, "This is a lie. Not an approximation, not a simplification, a lie." The lecture hall goes silent. He asks the class a question. What is a field? Hands go up. Expected answers flow. A region of space where forces exist. A vector quantity at every point. The thing that mediates electromagnetic interaction. Feynman writes each answer on the board. Then beneath them, in letters twice as large, he writes, "These are all descriptions of what fields do. None of you told me what a field is." The problem, as Feynman saw it, was this. Physicists had spent 70 years building incredibly sophisticated mathematical machinery to calculate field behavior. Maxwell's equations, vector calculus, tensor formulations, all magnificent tools. Students memorize div E equals RO over epsilon 0. They could solve boundary value problems, calculate pointing vectors, derive wave equations. But somewhere in all the mathematical virtuosity, everyone stopped asking whether fields actually existed, not as mathematical conveniences, as physical things occupying space. Back to that Cornell classroom. A student, his name was David Merman, later a distinguished physicist himself, asks the obvious question. "Professor Feynman, are you saying electromagnetic fields aren't real?" Feynman's response is documented in Merman's 1989 memoir. He said, "I'm saying you've been taught to think they're real, without anyone ever defining what real means in this context." Then he does something unexpected. He asks them to explain what fills the space between a magnet and a paperclip. The answers come fast. The magnetic field. Lines of magnetic flux. Field vectors at each point. Feynman waits. Then, "You're using the thing you're trying to explain as the explanation itself." This is where it gets uncomfortable. Because what Feynman revealed next, documented across 3 consecutive lectures in November 1964, contradicted 70 years of physics pedagogy. He walks them through the history. Faraday, 1831, discovers electromagnetic induction, doesn't know mathematics, thinks in pictures, imagines lines of force threading through space. Useful metaphor. Maxwell, 1865, translates Faraday's intuition into equations. Even more useful, the equations work magnificently. They predict electromagnetic waves. They unify electricity and magnetism. They're confirmed by every experiment. But here's what happened. According to Feynman's analysis, physicists started treating the mathematical field, a calculational device, as if it were a physical substance permeating space. The map became the territory. But then, and this is the part that makes physics professors uncomfortable, Feynman points out that you can derive the exact same predictions using an entirely different framework. He introduces what he calls the potentials first approach. Instead of saying electric and magnetic fields are fundamental, you treat them as derivatives of more fundamental potential functions. Same experimental predictions, same physics. Completely different ontology. The electromagnetic field in this view isn't a thing vibrating through space. It's a mathematical relationship between potentials. A student asks, voice uncertain, "So, which one is true, fields or potentials?" Feynman's documented response: physics doesn't answer which is true. Physics answers which is useful for this calculation. The lecture hall erupts. Students who spent 4 years memorizing field theory suddenly realize they've been operating on hidden assumptions. One student, this is recorded in the lecture notes archived at Caltech, says, "But professor, you wrote a whole textbook on quantum field theory." Feynman grins. That grin is described by multiple witnesses. He says, "I wrote a textbook on quantum field theory mathematics. Don't confuse the math with what's actually happening in nature." To understand why this bothered Feynman so deeply, we need to go back to his MIT undergraduate days, 1936. He's reading Dirac's Principles of Quantum Mechanics, the most abstract physics text in existence. Dirac introduces field operators, creation and annihilation operators, second quantization, brilliant mathematics. But young Feynman keeps asking his professors, what's being created? What's being annihilated? No satisfying answers, just, don't worry about it, the math works. This frustration haunts him for decades. By the time he's teaching at Cornell, he's determined his students won't graduate with the same hollow understanding. This wasn't just about electromagnetic fields, but about how physicists mistake mathematical formalism for physical comprehension. The distinction matters, because when you memorize, the electromagnetic field has energy density. U equals epsilon 0. E squared over 2 plus B squared over 2 mu 0. You're learning a calculational recipe. When you ask, what is this energy? Where is it located? Does it have independent existence? You're doing physics. Feynman's entire pedagogical mission was forcing students into the second category. He demonstrates this with a thought experiment, documented in Lecture 2-11, 2 charged particles in space separated by distance. Conventional explanation: Particle A creates an electric field filling all of space. Particle B feels this field at its location. Field does the mediating. Feynman's alternative: Particle A has a potential function that determines Particle B's behavior according to action at a distance. No field needed. Same predictions. He writes both mathematical frameworks on the board, side by side, asks the class which is really happening. The silence lasts 30 seconds, because they're realizing there might not be an answer. But then, just when students think they're getting comfortable with maybe we can't know, Feynman introduces retardation. This is where it gets genuinely strange. When particle A moves, particle B doesn't respond instantly. There's a time delay, light speed delay. Something has to carry the interaction across the gap. Now suddenly the field framework looks more physical again. Information propagates through space at finite speed. That propagating information, that ripple of influence, isn't that what we mean by a field? Feynman's response is documented in his correspondence with John Wheeler from 1965. Or it means space-time geometry itself carries the interaction, and what you call a field is just your description of curved spacetime's effect on particle trajectories. This reveals why most physics students memorize without understanding. They're taught to solve problems, not question foundations. A student can graduate with a physics PhD, publish papers using quantum field theory, calculate Feynman diagrams with facility, and never once ask, what ontological status do these fields have? The education system actively discourages the question. When students ask it, professors say, that's philosophy, not physics, or the math works, that's what matters, or you'll understand after you've solved more problems. But they won't. Because the understanding they're seeking doesn't come from more calculations. It comes from admitting that physics is built on useful models, not metaphysical truths. You've experienced this exact confusion if you've ever studied quantum field theory. The textbooks tell you particles are excitations of underlying quantum fields. Photons are excitations of the electromagnetic field. Electrons are excitations of the electron field. Clean story. Makes intuitive sense. Then you learn quantum fields are operator value distributions on space-time, not physical things, mathematical objects. So, what's being excited? The textbook moves on to calculating scattering amplitudes. Your question hangs unanswered. Feynman's approach to field explanation was fundamentally different from every physics textbook written before or since. He refused to use field lines, called them a crutch for people who can't think in vector calculus. He refused to treat Maxwell's equations as fundamental laws, called them useful summaries of electrostatic and magnetostatic observations, plus the displacement current term Maxwell added to make waves work. Most radically, he refused to say whether fields exist or not. He said the question was scientifically meaningless until you defined exist precisely enough to make testable predictions. But here's what he did teach, and this is documented across hundreds of pages of lecture notes. Think in terms of what's measurable. You can measure forces on charges. You can measure energy and momentum transfer. You can measure the trajectory of particles. Everything else, fields, potentials, virtual particles, wave function collapse, is interpretive framework, useful or useless depending on the problem. The greatest physics error is mistaking your interpretive framework for reality itself. A student asks, documented in the lecture archives, so electromagnetism isn't real? Feynman's response is worth quoting in full. Electromagnetism is as real as anything we know. But when you ask whether the electromagnetic field is real, you're asking whether your particular mathematical description corresponds to something ontologically primitive, and physics has no method to answer that. He continues, the field is real in the sense that it lets you calculate real effects. It's not real in the sense of being the unique, fundamental way nature operates. Nature doesn't care about your mathematical description. This created an existential crisis for serious physics students. Because if you can't say what fields are, how can you claim to understand electromagnetism? Feynman's answer: you understand electromagnetism when you can predict electromagnetic phenomena using whatever mathematical tools work best for the problem. Sometimes that's fields, sometimes that's potentials, sometimes it's Feynman diagrams representing particle exchange. The physics is in the predictions, not the ontology. The same principle applies today when MIT physics students memorize Div-Grad-Curl operations, but freeze when asked, what does divergence mean physically for an electromagnetic field? They can calculate it, they can't explain it, because they learn the mathematical operator without learning why that operator captures something meaningful about field behavior. The divergence of E tells you about charge density. But what is the divergence as a physical process? Most students have no answer. They were never taught to ask. This connects to a broader crisis in modern physics education. Online courses show beautiful animations of field lines morphing through space, slick visualizations of electromagnetic waves rippling outward. Students watch these animations and think they understand fields. But visualization isn't understanding. Feynman proved this in a brutal demonstration witnessed by his Caltech students in 1975. He shows them an animation of a classical electromagnetic wave, oscillating electric and magnetic field vectors perpendicular to propagation direction. Standard visualization. Then he asks them to calculate the wave's energy density using the animation. Nobody can do it, because the visualization shows field magnitudes, not field intensities, shows perpendicularity, not the phase relationships needed for energy calculations. The animation is aesthetically pleasing, but physically incomplete. You've felt this if you've ever watched a PBS Space-Time episode on quantum field theory and walked away feeling like you learned something, only to realize hours later you couldn't actually explain any of it. The video gave you the illusion of understanding through compelling visuals and confident narration. But genuine understanding requires confronting what you don't know. Feynman was merciless about this. A student once told him, I think I understand quantum field theory now. Feynman's response, tell me what happens when an electron emits a photon. The student launches into the textbook answer about field operators and creation operators. Feynman interrupts, no, tell me what happens, not what the math says, what physically occurs. The student can't answer, because nobody can. The math works. The physical picture is interpretation. This is why physics graduates often feel like frauds despite their degrees. They know how to manipulate symbols. They've solved problem sets, passed exams, maybe published papers. But when pressed on what quantum fields are, or whether virtual particles are real, or what the electromagnetic field is made of, they realize their understanding is hollow. They've been calculating without comprehending. And that hollowness, that gap between facility and understanding, creates profound imposter syndrome. Feynman's field pedagogy was designed specifically to prevent this, not by giving students answers about what fields are, but by teaching them to recognize when they're confusing mathematical models with physical reality. To be comfortable saying, I don't know what's ontologically primitive here, but I can make predictions. To distinguish between operational knowledge, knowing how to use field theory, and metaphysical knowledge, knowing what fields fundamentally are. The first is achievable, the second might not be. He demonstrated this distinction in his final lecture on the fields at Cornell, December 1964. He puts two frameworks on the board, Maxwell's field theory on the left, Wheeler-Feynman absorber theory on the right. Both reproduce all electromagnetic phenomena. Both are mathematically consistent, but they have completely different ontologies. Maxwell, fields are fundamental, particles respond to local field values. Wheeler-Feynman, direct particle interactions with advanced and retarded influences, no fields needed. He lets the class sit with this for a minute. Then, both frameworks work. Both make identical predictions for every experiment you can design. So, which one is true? The class expects a trick answer. But Feynman's response, documented in student notes archived at Cornell, the question assumes nature picks one mathematical description as its operating system. That assumption is probably wrong. What he was revealing, though he never stated it this bluntly, was that physics isn't discovery of what nature is. Physics is construction of models that predict what nature does. The distinction seems semantic until you realize it changes everything. A discovery paradigm says, find the true equations, they reveal nature's essence. A modeling paradigm says, build predictive frameworks, they reveal nature's patterns. Fields might be useful models. They might not be fundamental constituents of reality. The question is scientifically underdetermined. This philosophical position solved the problem that had plagued Feynman since MIT, how to do physics without getting trapped in metaphysical assumptions. You treat fields as tools. When field formalism gives clean calculations, use it. When it doesn't, use potentials or path integrals or whatever works. Switch between frameworks fluidly. Never commit to one as the truth. This pragmatic approach let Feynman make extraordinary discoveries: quantum electrodynamics, path integral formulation, Parton model, precisely because he wasn't locked into any single ontological framework. But it creates a deep tension for students trained to seek the answer. Modern physics education promises you'll understand how nature works. Feynman's honest version. You'll learn to predict how nature behaves, and you'll realize nobody knows why these predictions work. The electromagnetic field might be a fundamental feature of spacetime. It might be an emergent phenomenon from deeper quantum processes. It might be a useful fiction that happens to match measurements. Physics can't currently distinguish these possibilities. The same crisis appears in modern physics beyond electromagnetism. String theorists can't say whether strings are real or mathematical constructs. Loop quantum gravity theorists can't say whether spacetime is fundamentally discrete or whether discreteness emerges from their formalism. Quantum information theorists can't say whether information is fundamental or derived. Every frontier of physics hits this wall: powerful mathematics, unclear ontology. Feynman saw this pattern early and built his entire teaching philosophy around it. Don't pretend you know what's fundamental. do predict what's measurable. Yet, here's the uncomfortable implication. If fields aren't necessarily real, and potentials aren't necessarily real, and we're just building predictive models, then what separates physics from sophisticated data fitting? Feynman's answer, from a 1982 lecture at Caltech. The difference is that physics models are constrained by deep symmetries and principles: relativity, quantum mechanics, gauge invariance. These constraints aren't arbitrary. They seem to reflect something fundamental about nature's structure, even if we don't know what that something is. The models aren't arbitrary, even if their ontology is uncertain. This brings us back to that BBC interview with Christopher Sykes, when Feynman says, "I can't explain that attraction in terms of anything else you're familiar with." He's not admitting ignorance. He's rejecting the premise that explanation means reducing one phenomenon to other familiar phenomena. Real explanation, in Feynman's view, is building a mathematical framework that successfully predicts observations and connects to other frameworks. Magnetic attraction connects to relativity, quantum mechanics, gauge theory. Those connections constitute explanation, even without a mechanical picture of how magnets pull. The problem is, students are never taught this. They're taught to crave mechanical intuition. They want to visualize field lines, imagine force carriers, picture virtual photon exchange. When the math gets too abstract, quantum field operators, gauge transformations, path integrals, they feel like they've lost understanding. But Feynman would say they had an illusion of understanding before. The mechanical pictures were crutches. True physics understanding is knowing which mathematical frameworks apply to which phenomena and why those frameworks are constrained the way they are. You're experiencing this right now if you studied physics and feel vaguely fraudulent about it. You sense the gap between what you learned and what you truly understand. That gap exists because physics education optimizes for problem-solving ability, not conceptual clarity. You can solve Maxwell equations without understanding what solutions represent. You can calculate Feynman diagrams without knowing if virtual particles exist. The system rewards calculation, not comprehension. Feynman tried to fix this at Cornell and Caltech. The fact that physics pedagogy hasn't changed in 60 years suggests he failed, or succeeded so thoroughly that physics departments couldn't handle the implications. Because accepting Feynman's view means accepting that much of what you learned as how nature works was actually, here's a useful model. It means recognizing that fields, particles, waves, and forces might all be equally valid or equally provisional descriptions. It means living with ontological uncertainty while maintaining mathematical precision. Most physicists can't do this. They need to believe their framework is true, not just useful. Feynman's genius was not needing that belief. His pedagogy tried to cultivate the same freedom in students. It rarely worked. Human psychology craves metaphysical certainty, even when science can't provide it. The final implication: if you can't say what electromagnetic fields fundamentally are, you definitely can't say what quantum fields are, because quantum field theory is built on top of classical field concepts. If the foundation is instrumentalist, fields as useful models, then quantum field theory inherits that status. This bothers physicists who want quantum field theory to be the fundamental theory. But Feynman's analysis suggests it's one framework among potentially many. Effective, powerful, predictively successful. Not necessarily describing what's ontologically primitive. Feynman's approach to another concept,